Okay, as we begin to understand bonding, one of the things that we could be asked to do is to calculate the amount of charge on the atoms in a bond. So let's take a look at problem 8.90 to help us see how this can be achieved. So in 8.90, it says the dipole moment of HF is 1.83 d, or dBi. Now, a dipole moment is given a mu, and it is then told to us that it's 1.83 dBi. So this is the dipole moment, and it's given to us. Remember, dipole moments occur when the electrons are not shared equally in a bond, and so they are pulled toward the atom with higher electronegativity. And this separation of the charge between the positives and negatives as the electrons move toward one of the elements creates a dipole moment. Now in this problem, they also give us a bond length. They tell us the bond length. The app did something funny on me. They give me a bond length, which is R, and they give me it as 91.7 picometers. Now, actually, in the textbook, it says 917 picometers, but I investigated this and discovered that there was a typo. So in problem 8.90, it should be 91.7. And this is the bond length. Now, there is an equation that helps us relate bond length to dipole moment, and it is the dipole moment equals the charge on the atom times the bond length. So this question is asking us to determine the charge here, which is written as Q. It's not the same as heat. And so we can use the equation, rearranging it, to see that we will need Q would equal the dipole moment divided by the radius. Now, dBi, in order to calculate this and move it into the units, we need to change the units of dBi, or D, into coulombs times meters. So let's do that. The relationship between the two things is 1D equals 3.34 times 10 to the negative 30 coulomb per meters. Now the reason when we're dividing by the radius, it's going to be in units of meters, and so we need to be able to cancel. So first let's convert our dipole moment. So 1.83 d times 1d on the bottom, so they cancel, and 3.34 times 10 to the negative 30 coulomb per meters. So if we multiply these two things, I get 6.112 times 10 to the negative 30 coulombs per meter. Okay, well, and I'm also, so now I think we're ready to plug in for the charge. So Q would equal, we'll put the dipole moment on the top, which we said is 6.112 times 10 to the negative 30 coulomb times meter. And then we'll put the bond length on the bottom, which is 91.7. Now it's a picometer, and pico means 10 to the negative 12. So I'm going to convert that into meters by multiplying by 10 to the negative 12 so that my meters will cancel, you see here. Now this answer gives me then 6.665 times 10 to the negative 20 coulombs. Now the answer, looking at this problem further, the answer wants us to convert this number into the units of electronic charge units. So let me move to the next page. And I'm going to rewrite that number. So what we have, whoops, my app is doing something again. Okay, what we have is Q equals 6.665 times 10 to the negative 20 coulombs. I know that one electronic charge unit equals 1.602 times 10 to the negative 19 coulombs. This is a relationship that I looked up in the book, and just like the Debye units to coulomb per meters and this one, not something I have to memorize, just something I looked up. So now I'm going to convert. So I take the answer that I had calculated previously, and I will put the coulomb on the bottom so that it cancels. And when I do this, I get 4.16 times 10 to the negative 1 e, or I could rewrite this as 0.416 e. Now, I have the molecule HF. So it may be, if I want to know the charge on each one of them is going to be positive and one of them is going to be negative. The more electronegative element, which in this case is fluorine, will attract more electrons, so the charge on it will be negative 0.416 e. The hydrogen will have the same charge, but it will be opposite in sign, so it would be a positive 4.16 e. So that would be the actual charge and electric charge units that are on the molecule in HF.